For trace elements, you are looking at transition metals, basically. Right? So, if you take like fourth period transition metals, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, all of those would...
Selenium and sulfur?
Selenium, sulfur is more prevalent. Selenium, iodine, bromine, very, very unusual in some marine animals, but it's mostly transition metals. That's what they're shooting for. Okay, and then beyond that, is molybdenum. That's it. Okay, anything else beyond that is toxic to living organisms. Just working this periodic table, there's a subset of 20, 25 elements that we find that account for 99.99% of what's in living organisms, and most of the other stuff is toxic, basically. Okay, questions? Okay, you have to ask questions. There's another anatomy review session.
Another question.
Yeah.
Okay, so question 13.
Sorry about that. So here's your packet. Issues.
Okay, now, for this question, we don't want to estimate the pH using strong acid or strong base after you put the acid.
Well, this gives you, it's a two-component phosphate buffer, so you would have to figure out the split in between. Alright, so let's solve this one, alright?
Okay.
So it says, protein purification protocol calls for 1 liter of 50 millimolar phosphate buffer, pH 7.2, 500 millimolar sodium chloride, okay? For cation exchange chromatography step. We'll be doing that next semester with some of you, okay? That's it. And we'll have to mix that. And that's it. Those are instructions, okay? That's what the procedure says. We used this as buffer A. Now you go ahead and repeat the experiment, okay? Enough information is given to you to repeat the experiment. How you make buffer, you should know. You're a chemist at that point, okay? For biology. So I say describe in detail if it's bolded, underlined. I really mean it. Kind of like I want, procedure of 10 steps saying how are you gonna do it, not just 2 numbers, okay? Which may or may not be correct. So to describe in detail, you have to start saying, well, I will go and weigh out this much, and then I will dissolve it. I will bring volume up to about 80%, adjust pH, if necessary, filter degas, put into labeled bottle. Okay, that's what I expect as a description. Now, the first step is, well, how much should we weigh out? Okay, or in this case, how many milliliters of these stock solutions should I use? Right? So this is phosphate buffer. When we say phosphate buffer, it's really the dihydrogen phosphate and hydrogen phosphate combo of conjugate acid and base. You are given stocks of those. So you have disodium hydrogen phosphate and potassium dihydrogen phosphate, 1 molar solutions. Okay, now bottles in the shelf ready for your use. And also sodium chloride will be provided. It's an ionic substance, so it has the formula unit weight given to you, 58.44 on the label of the bottle itself. Okay, and that one is obviously solid. We would get from stockroom, and we have light chemical level. Okay, pK values are given. That's all we need. So to figure out, let's do sodium chloride first. So we are trying to figure out how many grams of substance should we weigh out so that we make solution of a given molarity. Okay, so let's have mnemonic here. Molar mass, molarity, volume. Okay, in proper units. They have to be multiplied together. If you want to set up this as a conversion factor, please do so. However, exam is not the time for figuring these things out. Okay. So it says 1 liter, 500 millimole, okay, for sodium chloride. And molar mass was given, 58.44 grams per mole, times 0.500 mole per liter. That's the concentration that they want us to have for that salt, times 1.0, let's assume expressing significant is 0 liters. Okay, 1 liter of 500 millimolar solution of sodium chloride. That's one component. And that's it. Okay, after that, you don't need a calculator really. If you think about this, you just divide this by 2, right? Okay, so 29.2. And of NaCl, solid salt. Okay, let's double check, just in case I can do math. Seems fine. Right, so you would go to balance and weigh off this much and have it on your dish, put it into a beaker that can hold at least 1 liter liquid at the end of the process. Okay? Next, you have to figure out that buffer agent. Okay? So in this case, you are given 2 components. You are given conjugate base solution and conjugate acid solution. So you'll be bringing them up in proper ratio to end up at the proper pH. Okay, or close to it anyway. Okay, these things only work in theory anyway. You have to find just pH at the end of the process anyway. Okay, so the reason is for that because phosphate buffer pKa depends on temperature dramatically and concentration both. Okay, and it's a 2 complex 3-dimensional function of those parameters. Okay, so it's like whatever you do, it's approximate, and then you fine adjust your pH to the temperature at which you will be using it. All right, so the point is to get 50 millimolar, obviously, and yeah, you don't want to. You already have solutions ready, so you'll be pipetting a certain amount of milliliters. So it's a buffer problem. So right now your Anderson-Hasselbalch equation. Okay, that gives you half point. Well, I'll pretty much give you the thing on the cheat sheet, so I'm not even there. Right. It's a buffer problem, so put it down, okay? Something's gonna come up to you. So pKa is given to you. Actually, 3 pKas are given to you. Which one would you use?
6.86.
Alright, so something that's close to the target pH. Remember, buffering region is plus minus 1 unit around pKa value. So if we are shooting for 7.2, we should be shooting for second one, which tells you it's going to be dihydrogen phosphate as acid and hydrogen phosphate as base for this particular system. Right? And then, so pH is given, pK is given, and now we have to get the split out. Okay, so let's figure out the split. It's a base to acid. Alright, so this will be 10 to, we said pH minus pKa. Okay? So that's the formula that comes out of the algebraic manipulation of this. You can start putting numbers here. So this is 7.20 minus 6.86. Okay, now where did I get that 6.86? It's a painful multi-year experience. Yeah, and it gets you close, but it's not perfect because it's temperature and concentration dependent at the end of the process anyway. Alright, so, okay, so let's do that. So at this point, I guess you do need a calculator because this would be hard to actually do in your head. Alright, so 10 point, now it's what, like 0.34? Alright, so I got 2.188. Okay, there's a ratio between base and acid. Does it make sense? 50-50 would be at 6.86. I'm on the basic side of 50-50, so I have to have more base, which that ratio tells me. Okay? And so now the trick was, alright, divide it by 1 and figure out your split. Okay, so your split would be 2.188 over 3.188 times 50 millimolar, and then this would be 1 over 3.188, okay, times 50. Now this trick just basically skips solving system of 2 equations with 2 unknowns. gives you answer directly, okay? And so technically it's a 2.188 divided by 3.188. So 68.6% of this one times 50, because we are going out of 50 millimolar, okay? So I need 34.3 millimolar, which will be, because I have 1 molar solution and I'm making 1 liter of it, it will be 34.3 milliliters of base. Okay, so dipotassium, hydrogen, phosphate solution that I have available. So I should say of 1.0 molar. Okay. Why do I use 1 liter and 1 molar solution? So that the math can be skipped. I don't have to worry about it. It's the same number. It's going to be milliliters. Right? And so this one, you could go subtract the above number from 50 to solve it, or solve it through this equation. Doesn't really matter. I'm going to subtract it from 50 myself. And so I'm getting 15.7 millimolar. And so this will be 15.7 milliliters of acid one. Okay, so NaH2. 1.0 mole. Okay, so that will be the answer. So technically, you have to weigh out this. You have to take a pipette and mix these amounts of those solutions together in the beaker. Bring the liquid to about 800. Fine adjust pH as needed. Okay, it should be close, but we may need a little bit of adjustment, 0.1 unit or so. And then finalize the volume. Okay. Now this is buffer for purification. Okay, so 3% error makes no difference. So we don't really need volumetric flask, rigid cylinder will do for this one. And then typically you filter it, degas it, and store it in labeled bottle. Okay, and so those are steps you should kind of mention in that detailed description. Yeah.
How do you know which one's the acid and which one's the base?
Acids donate protons, they have to have them. Now in this case you have a system that has 2 protons versus 1 proton. Conjugate acid-base pair differs in 1 proton. Once acid donated proton, it's missing it, so this one was acid, it had 2. This one is conjugate base of it, it has 1 less.
Well, in the text it says Na2H2O4.
Let's see, Na2, I see, okay. That's just counter ion thing. Na2, okay. It's a counter ion, okay? That's the species that is floating there. I don't recall, don't remember it correctly. Yeah.
Would the sodium and the base react with that mixture?
I'm sorry?
Would the sodium and the base react with the NaCl that you're adding? Like, is there some kind of relation?
Okay. Not really. Chloride is conjugate base of strong acid, so it's a very weak base. Yeah, sodium, chloride, and potassium in this case are counter ions. Floating around, not really caring too much. Okay, they're spectator ions, as we call them. Okay, you always have some salt in living organisms, so it's nicely biocompatible. Okay, did the key come up with the same answers? Yep. Okay, good. Alright, so this is what it takes. You will have problem like that, give or take, on the exam. Right, so make sure you try several of these, look in the textbook. Is this trick that you need to pick up kind of thing, otherwise you're stuck with solving a system of 2 equations with 2 unknowns, which nobody has. It's not the math test, it's a biochemistry test, okay? It's a applied biochemistry problem. Okay, we will do this in lab every single time you show up in the lab next semester, and even this semester. Okay, more questions? Yeah.
Can you explain again what hydrophobic effect is?
Okay, so we talked about hydrophobic effect in connection with weak intermolecular interactions, and what I said was that it's not one of the weak intermolecular interactions. Okay? Essentially, what hydrophobic effect is, it's entropically driven effect that separates materials with incompatible weak interactions from each other. Okay, idea is this. Let's say you have water and oil. Okay, you kind of know these things don't mix. Well, why is it that they don't mix? And the molecular explanation for it is this. Okay, water molecules can form hydrogen bonds to each other. So they really like to hold each other very strongly. Now, oil molecules are hydrophobic. They can only form, at best, weak dipole-dipole interactions, but mostly nonpolar London forces is what you get. Right? No hydrogen bonds between each other. Okay? And water has very limited amount of hydrogen bonds it could form to fat molecules. Okay, per whole molecule, basically you can neglect it. Right? So technically we are talking about incompatible intermolecular interactions. So if you put these materials together, okay, as a bulk, what's going to happen is these water molecules will hold each other and won't let anyone else in their midst, because they're holding each other so strongly that those other ones that can only form London forces are not going to get there. Now, if you started from different situation, if you now violently shaked it so that you mix these things at kind of like molecular level, okay, what would be happening? Well, these water molecules, these hydrogen bonds, would get disrupted, and some of these nonpolar molecules would go in. Okay. However, because water molecules are trying to form these much stronger interactions, they would eventually find each other and displace these nonpolar molecules away from them. Okay. Now, you could describe that as they're trying to minimize the surface exposure between nonpolar and polar surface. Okay, and the solution is to basically minimize the surface, and that really leads to expulsion of these nonpolar materials from the polar liquid. Okay, and that's what we call hydrophobic effect. It's now why we say it's entropically driven. Well, because technically entropy of the system will be increasing, doing so. And the reason for that is that these water molecules, when they are stuck on the surface of nonpolar droplets or something like that, that may be dissolved or dispersed in that liquid, will have lower entropy compared to situations when they are free to float in liquid water. Okay? When they are exposed to the surface of these nonpolar molecules, they are basically, they have to kind of be in this particular position. They can rotate around and move around, okay, because the other side is not providing those hydrogen bonds that would allow them to do that motion. Okay, so they are kind of stuck in place in a way, okay, and that's lowers the entropy. So if you now minimize the surface exposure, they can go freely into the bulk of liquid, increasing their entropy. So overall, there's entropy increase when you separate those phases from each other. Okay, and we see that happening in biological membranes. We see that happening during protein folding, for example. Okay, that you can achieve much higher organizational state for the polypeptide chain, but for a system, because of water entropy increased so much, it's still favorable thermodynamic solution. Okay, now, if you were to look at, well, what kind of intermolecular interactions hold that system together, at that point you would be saying, okay, there are hydrogen bonds, up to hydrogen bonds in liquid water, London forces in nonpolar solvent, and then on the periphery you would have some, dipole-induced dipole interactions, okay? But hydrophobic effect is not an interaction per se, okay? It's the effect driven by entropy increase of the system that can be explained by this. Is it clear? It's a pickle. You just have to look at it multiple times, see what the reasoning is. It's the optimization of the surface exposure between these materials with non-compatible intermolecular forces.
Water pulls extra hard on water and squeezes everything else out.
Pretty much, yeah. Water, because waters can bind each other strongly. They just squeeze other things out. That's what it is. Okay, and now that is actually, can be also looked at from this entropic point of view, that these water molecules that were before on the surface now are in the bulk of water and they can do whatever. So there's enthalpic and entropic, but the entropic effect is really what we care about. Yeah.
How do you do question 10? It's the figure out how many proteins can fit in the cell. And understand and see if I know
Yeah.
I don't fully understand.
Well, just let's see. So let's see. It says how many glucose molecules does a spheroidal bacterium with diameter of 1 micrometer contain when internal glucose concentration is 1 millimolar? Okay. Right. So, okay, this is just simplistic, kind of like, what is this about? This is basically saying cells are kind of like factories, okay? They have stuff in them. Now the question is how much stuff? Okay, get some kind of like, how many molecules are we talking about inside cell kind of? All right, so we are taking really tiny bacterium, okay, really tiny, that's a really, really smallish, to keep things simple, okay? So 1 micrometer, and I'm saying spherical, so we will go with sphere, and, all right. So this is Jenkins problem, really, if you think about it. Okay, this is basically saying you have volume, you have concentration, and how many moles and molecules is that? That's chapter 3 in Jenkins, basically. Okay? So let's start with volume. So let's figure out that volume. Okay, what is my volume? So it's a sphere. So 4/3 times
Pi r cubed.
r cubed times pi or something, right?
Yeah.
435 times
Is what?
Cubed. He's got.
It's a spherical, not cube.
No,
It's a spherical bacteria, okay?
No, I'm saying the r is cubed.
Yeah.
You're good. I was saying you're right. You're good.
Yeah, okay, yeah. So that's the formula, and I gave you the formula,
Mhm.
okay? So, yeah. So you could figure out at this point, it's a 4/3 times, 3.1415 times, and now it's a micrometer diameter, okay? So this is radius. So you would say 0.5 times 10 to minus 6 meters. That's a micrometer, and now this should be cubed, right? So, calculator. Come on here. So let's see, 0.5 minus 6 cubed times 4 divided by 3 times 5. Okay, so I got 5.23, let's get extra digit here, times 10 to minus 19 cubic meters. Okay? That's what I got here. Okay. And now, so you are given volume, so let's continue with that number. 3.6 times 10 to minus 19 cubic meters. Now, it would be nice to go to liters. So cubic meters to liters. How many liters do you have in cubic meter?
1,000.
1,000.
How many?
1,000.
1,000, right? So it's a liter is a cube of 0.1 liter. So you have 10 of those along every edge. So 10 times 10 times 10 is possible, right? Times, okay, so we have liters now, and now you have molarity given. Okay, molarity of glucose in this case was 1 millimolar, it says. Okay, now glucose is more like 5 millimolar in blood plasma in humans, but again, let's say millimolar. Okay, there's a lot of things that are millimolar. So it's a liters, moles, and now we are saying 1 milli, so that means 1 times 10 to minus third. Okay, now, so our liters are gone. We have moles of glucose, and we are talking molecules. So Avogadro's number. Okay, so here you would say moles, molecules, or objects of any type. 1 mole has Avogadro's number for those molecules. So 6022 times 10 to 23rd. Okay? Now that's why I wanted a calculator here, because this has crazy looking numbers. So times 1000 times 001 times 6.022 to 23rd. So I got 350,000 here. Okay, approximately. So think of cell as a city. Okay, so these are people in the city. You see? So how many schools do you have in that city? That's what the next question is. Okay, if you had micromolar concentration, okay, for something, it'll be less, right? By 1,000. So for micromolar, this would be 315 of objects, whatever that means, schools, okay? And how many post offices do you have in the city? Okay, that's another order of magnitude, or a couple of orders. So basically, if you have nanomolar, you are getting 3 here. Okay, so 1 nanomolar will give you about 3. 1 micromolar, anything will give you about, so hundreds, tens, ones, right? So if you are talking about, let's say, how many DNA polymerases you have, you are counting, couple, okay? If you are talking about small molecules floating around, amino acids, glucose, those kind of hundreds of thousands of those. That's kind of what gives you a picture here. Okay, so larger, more complex molecules, you will really only have 3 or 4 of those per whole cell. And those have to do the job, okay? That's why they do it fast, but it takes a while for them to finish the job because there's just a couple of them. Okay, so some proteins. So anytime you hear that, okay, something is nanomolar in cell, that's like a couple of things per cell. Now, eukaryotic cells may be 1,000 times larger in volume. Okay, so these things will scale up, obviously. But for bacteria, bacteria are living objects, all right. You will have just several, low dozens for proteins. All right? So if you have an enzyme of glycolysis, well, you've got 50 of those there. If you damage them, the whole thing is going to die. So, because you have to remake those. Okay, you have only a very limited amount of this. Okay, is that clear? So basically, the only thing was, okay, you had to compute volume from, some geometrical formula, but anything beyond that was just conversion of units, solution, chemistry, application of molarity, and then chapter 3 when you talked about moles. Okay, more questions? Yeah.
Question 23.
23. 1, 23. Okay. So structure is shown, and it says, well, what kind of glycosidic linkages are found in this polymer? Okay. So now these zigzag lines here suggest, okay, repeating unit that is shown to you keeps repeating, and it's being connected by those zigzag looking lines, right?
Okay, so you just imagine that
Yeah, it continues. Okay, this unit is over and over and over and over and over and over again. Okay, that's what it is. So keratan sulfate is one of those glycosaminoglycans we mentioned occur in all kinds of weird structures. Right? So if you look at the middle one, so this is a standard position Howard projection. So going up means beta for D sugars. Let's check that. Both of these sugars or sugar derivatives are D, so I can use that rule. So this is beta, Now this doesn't have any other carbon on it, so it's a beta 1. And it goes to carbon 4. So this connection is beta 1,4. Now this connection here is going up, so beta, it's aldose like sugar derivative, so beta 1, and it goes to, and it connects to what's into the carbon 3, so beta 1,3. Huh? So this is the option of that type, so B seems to be.
So if we think of the ring as being like a flat surface, this thing would be shaped like a spiral staircase.
It would have to be offset, but otherwise you
Yeah,
have
like these ones would be like this,
Yeah.
but then the next one would be slightly round this way.
Yeah,
and then-
yeah. If that was the case, that's what that zigzaggy looking glycosidic linkage means. Okay, this kink here, it doesn't mean there is CH2 group there. Okay,
Mhm.
our projection, we just do these connections to keep, if you want to keep them in kind of like a line looking arrangement, that's what you have to do to those bonds. All right? If he's basically saying to keep these bonds looking straight, we would have to offset them into staircase-like looking structure. Yeah.
Can you go to 26?
Okay, 6. Categorize these as hydrophilic, hydrophobic, or amphithetic.
So